Okay, it is time to start. Hello, everybody. Good afternoon. I hope you have been enjoying the conference so far. Is it? Yeah, great. Thank you. Okay, my name is Giuseppe D'Angelo. I work at KDAB. I'm a software engineer. I work on a lot of Qt-related projects, so I decided to share a little bit of my insights about what is the best way I think you should be using Qt these days. The title of the talk says Effective Qt 2017 edition. What's the deal with that? Well, the title, Effective, of course, is pays homage to Scott Meyer's series of books. So in this talk, I'm going to present advices, just like one sentence or two sentences, and then I'm going to explain why I think you should be using Qt in one way or another. And the 2017 part is about the fact that the advice I'm going to give you is about today. It's the best thing that we can do at this moment, but especially you, if you're watching this video in 2039, please reconsider what I'm just about to say. Yeah, please verify that what I'm going to say still applies. So what is that we are going to say? We're going to discuss a few areas in which Qt and C++ as a language and as a library are moving. In particular, the areas that intersect the two are a bit of a gray zone right now. So I would like to shed some light about what to do. So we're going to discuss a little bit about Qt containers, what's the deal with them. In particular, we're going to discuss something called implicit sharing, a tool called Clazy. I discuss a little bit about Qt string classes, and then if there is time at the end, or if you ask the right questions, I've got bonus slides as backup. All right, so let's get started. Suggestion number 1, understand the Qt containers and prefer the standard library ones. Don't use the Qt containers unless you have to. So you already look shocked. Come on, you use Qt and you already immediately say, don't use Qt containers. What? Yeah, there must be something good in there. No, there is something to say about this. There is a whole story, so let me explain this point. Qt, if you don't know, so I'm just asking, how many of you are using Qt as of now? Yeah, I'd say the big majority. So you should know that Qt ships with its own set of containers. The reason why Qt ships its own containers are pretty much historical. Up to 5 years ago, Qt needed to work on platforms without a standard library. As surprising as that sounds, so such platforms existed, still exist. The second reason was that Qt did not want to expose standard library symbols from its binary interface, right? So Qt had to basically reinvent the containers to work around these limitations. Likely these reasons are historicals, because now since Qt 5, we require you to have a working standard library. But nonetheless, Qt still has its own containers. These containers are exposed by Qt APIs. And the thing is this, that these containers are eventually available for your own applications. So people who are using Qt naturally just find, yeah, okay, I got this thing coming from Qt. Why don't I use it also in my business logic, right? Well, that's the thing. That right part is not quite entirely accurate. So let me discuss about these Qt containers. Where do they come from? Qt containers are not just a reimplementation of the standard library containers or something like that. Qt containers are drastically different from the standard library ones. In particular, some design decisions were made back then to focus more on ease of use and productivity for the average developer rather than being extremely strict and accurate and correct like the containers coming from the standard library. This snippet code shows a few differences, a few qualitative differences that you may see between the Qt containers and the standard library ones. So for instance, I'm here creating a QVector, so a vector of integers, and there is only one template argument to QVector, that's the data type it holds. There is no allocator, there is nothing advanced use case, just, okay, that's a vector of integers, period. How do I fill it in? Oh, there is this nice overloaded left shift operator that you can use to chain basically pushbacks into a vector. Yeah, that's nice to write. I can take a copy of a vector, so create a vector v2 from v1, from the first one, and that copy is cheap. We're going to see why that copy is cheap, but basically that's not a deep copy, that's just a ref counter increase. How do I check if a container contains a given value? Well, the answer for the standard library is use an algorithm. In Qt, we said, perhaps it's nicer if we could just add a few convenience member functions right on top of vector. So you can write something like if v2 contains a certain value, do something. Yep. And finally, Qt favors a certain kind of wording, a certain kind of expressiveness. So to check if a container is empty, you write is empty. You don't write empty, which might be ambiguous. Yep. So they're very different, as you may see. If you are used to see the C++ style of writing things, this style may surprise you. So what the containers do come with Qt? I made here a brief list of Qt and standard library containers, in particular the linear containers. They're not even all, but from the standard library there are even more. There are also the adapters. I just made a few. So in Qt we have qvector, which is a roughly correspondence of standard vector. It's a linear containers. Elements are allocated in a contiguous memory region. We got something called qlist in Qt, which has no standard library equivalent. Yeah, that is that. There is a linked list in both Qt and standard libraries. Standard library also now got forward lists, so single linked lists. And there is in Qt another guy called qvar_length_array, which does not have a corresponding container in the standard library. Then the standard library, as I said, has many more. There's deque, var array. It's got all the adapters, such as queue, stack, priority queue. There is var array. Those don't exist in Qt. When it comes to associative containers, Qt also has them, of course. There is map, there is multimap, there is hash tables, there is multiple hash tables, and there is a qset, which is not like standard set, but it's like an ordered set. So a qset is not ordered, right? It's just a set of elements. Let me spend just a couple of words about the couple of containers that Qt has and the standard library does not have. In particular, the first guy, qvar_length_array, what is it about? qvar_length_array, perhaps you've heard about it under another name, like small vector. It's a vector which pre-allocates a buffer internally, so that if you don't need to grow too much, this guy can avoid hitting the heap. It can store all the elements inside of it without allocating memory from the free store. Otherwise, it will allocate. Otherwise, it becomes just a vector. So this is extremely useful when you can know, in advance, yeah, I think that on average, I'm going to require up to a certain small number of elements. Let me pre-allocate them right inside the var_length_array object instead of allocating on the heap every time. And this can have some significant performance advantages. The other guy that Qt has and the standard library does not have is this guy, qlist. So first and foremost, what is qlist? It's not a linked list. There's nothing to do with linked list. It's like a vector. It's an array-backed list. But its behavior is very surprising. Depending on the type you put inside qlist, this can either be just a plain vector, so elements are located contiguously in memory, or can become an array of pointers to the elements. So each and every element gets allocated individually on the heap using operator new, and then the vector stores pointers to them. This difference, the fact that qlist has this surprising behavior depending on the type you put inside of it, and especially the fact that this may turn down to be just a vector of pointers to things, so have terrible performance, makes me recommend you to just avoid it, okay? In case you're very curious, I got some bonus slides about how qlist exactly functions. The recommendation for this one would be just avoid it. So let's go back to the beginning of this section. I said, understand the Qt containers, so here they are, and avoid them. But why? There's a huge number of reasons to avoid them these days. I would say that the first and most compelling reason is they're not actively being developed. You should not be using something that is not actively being developed, while, on the other hand, on the standard library container, we got a lot of activity, a lot of things going on. Yep. In general, the standard containers are faster, expand to less code, are more tested because they're also used outside of Qt. They're used by the broader C++ community. And of course, typically, the standard library containers you're using come from the very same people that are writing your compiler. So you know they're pretty well optimized. Yep. The features of the Qt containers are greatly inferior to the standard library equivalents. I made here a brief list of them, but actually I could go on for slides and slides and slides. To give you just a sample, the data types that Qt containers hold must be default constructible and copyable, which is a requirement that these days is really laughable. They have no exception safety guarantees whatsoever. Yeah. Several C++98 APIs are still missing. For instance, you don't have range construction and range insertion inside Qt containers. Most of C++ APIs are still missing. For instance, there is no emplacement. And all the post-C++ APIs are missing. For instance, all the node-based APIs, the now map and another map have got in the standard library. Yeah. In addition to that, of course, you don't have any flexibility when it comes to allocation, comparison, hashing. As I told you, all the various template arguments that you can use to instantiate a standard map, they're not there. You just allocate a map with a key and a value type. That's it. Yep. Inside Qt also got like inconsistent APIs. So for instance, there is a QVector append overloaded for R values. There isn't the equivalent for QList. Some people just forgot it or they didn't consider it was a good idea. In general, yeah, so all these reasons should make you very aware that you should avoid using Qt containers from your own code. Right, so which ones should I use? My recommendation would be for many important metrics, stick to the standard library containers. Yep, this recommendation is so good that actually Qt is already using standard library containers inside its own implementation. Yeah. However, there is this thing that Qt has a very strong API contract, so we cannot just change our APIs to take and return standard library containers. And for that reason, Qt still exposes its own containers at the API level. And my recommendation would be do the same. Prefer the standard library containers for your own code, especially for your business logic. Use Qt containers only if you don't find anything in the standard library that suits you, but that's very unlikely these days. And use them when you must use them, that is, when interfacing with Qt itself. That's the only moment where you really need to create a Qt container, to pass it to Qt APIs, to receive it from the APIs. So there is that. Consider using them when interfacing with the Qt rather than converting back and forth, because that's pointless. Word of advice, what's going to happen in a couple of years down the road when we're going to release Qt 6, that is the next major version of Qt, where we can break some API. I don't think we're going to break anything. I think that unfortunately, Qt will need to stick with its own containers in its APIs for a very, very long time to come. So there's that. We're just going to accept it. I hope that in a couple of years, we also have much better refactoring tools, so eventually we will be able to give something to developers to move away from the Qt containers in their own code. But until the moment comes, unfortunately, Qt containers are here to stay for the foreseeable future. So don't worry about them disappearing tomorrow just because I told you, hey, don't use this stuff. We're not going to remove it. Don't worry about that. Okay? All right. Suggestion number 2. So if you do need to use Qt containers, for instance, for interfacing with Qt, remember to use declare type info. Remember to declare some type traits for the Qt containers. So what's the story with type traits? And nobody told me that you needed type traits in order to insert a type into a container. Qt uses a few type traits to basically just optimize the handling of data types inside their own containers. And the most important optimization that Qt can do with a given container, with a given data type into a container is this one. Is when growing an array of objects of a given data type, can I just use realloc? Let me actually rephrase that. If I open a C++ textbook and I open the paragraph that explains how vector works, what happens when I come down to explanation when vector needs to grow and needs to realloc? Yep. The paragraph says this. The paragraph says what a vector is going to do is allocate a new chunk of memory, is going to move the elements from the existing chunk of memory to the new chunk of memory, possibly by using move if not except or something like that. If that works, vector is going to destroy the elements in the old copy, and it's going to deallocate the old copy. Those are all the steps that are necessary in order to resize a vector, right? If I open a C textbook and I come to the paragraph that discusses more or less the same, how do I reallocate an array? They just say use realloc. Realloc, what does realloc do? Realloc allocates a bigger chunk of memory, and if needed, it will copy the memory from the older one to the new one. So we just apply memcopy to the contents and move them in another position. There is no need to calling a code that invokes move constructors or copy constructors and destructors, right? However, there is a catch. Is it always safe to use realloc? Well, not always. This is safe to do only if the type is what we call relocatable. What does that mean? Relocatable is not a C++ trait, it's not a C++ definition. Relocatable means you can move this type in memory by using memmove, by using memcopy, without breaking instances of that type. And it turns out that many data types, especially all Qt value classes, so most of them, benefit from such an optimization because they are movable, they are relocatable in memory, and therefore you could just grow arrays of them by using realloc. So let me discuss this property, this relocatable, I will never be able to say that. Relocatable, okay, whatever. Can we relocate, better, this type in memory? Suppose I've got this type, which is a vector of integers, not templated, right? It's got a size, it's got a capacity, and it's got a pointer to the actual array. Can I move instances of this type in memory by using a memcopy or memmove? Pretty much, yes. I mean, assuming the implementation is reasonable, it doesn't do anything crazy, I could just copy these elements byte by byte in another position and obtain something that works. Yep. Let me ask something else. Can I relocate instances of this type? So this is like a pimple type. The type is just a pointer to a struct which contains the actual data. It's somewhere else in memory. Can I relocate this type? You say yes, but the actual answer is depends. It depends on something. It depends on whether the private part has a pointer back to the public one. Because if that's the case, you cannot relocate this in memory. Yeah, you need to patch that pointer. You need to run some code. So it depends. You need to know more about this. Yeah, if the private has a link back, the type is not relocatable. What about this one? That's like a node in some kind of tree structure. So the node itself has some data, then it's got a pointer to the parent node, and a list of pointers of the children. Can we relocate this? You see too many pointers. No, this is not safe. Yeah, indeed, this is not safe in general to relocate. We say that the address of such a node is its identity. We identify such objects by actually its address in memory. So that is definitely not safe to allocate, because moving in memory would break the pointers. How about this type? So this is like a string class. It's got, again, a size, a capacity, a pointer, and a buffer in there, like 32 bytes of data. Who says yes? Who says no? Who says depends? Depends is also good. Yeah, ultimately, the answer is, again, depends, because the real deal is what's the data thing there for? If that data is some sort of short string optimization, then you cannot move these types in memory, because begin may point to data. This is such an example of self-referential data type, a type that points into itself. So if you move it in memory, you're going to break it. However, if I'm using data from some extra data, a tag that I just attached to the string that has nothing to do with the actual string payload, then yes, this type is now relocatable. The point I'm trying to make here is this. The compiler cannot just look at a type and figure out if it is relocatable or not. You must tell the compiler. Only the author of a class knows. Yeah? It's just a decision on how you design your type. So for that reason, Qt and other libraries decided to add the type traits to tell the containers, yes, this particular type is safe to allocate in memory, this other type is not safe to allocate. The way we do that in Qt is by using that QDeclare type info macro. EASTL, which is an implementation of such library by Electronic Arts, has something which does exactly the same thing. It's called EASTL declare trivial relocate. Surprisingly, the standard library still haven't figured out how to do this in itself. So there is still nothing in the standard library for supporting this. I guess that adding it would make so many breakages all over the place, but yeah, I would try to insist because we want this into the standard library. So how do we use that Qt macro, that QDeclare type info macro? We use this way. We just write the macro, QDeclare type info, the type for which we want to declare the trait, and another tag which says something about that type. We got three kinds of tags. Let me start from the bottom one. The default is something that we call a complex type, a type that from which you cannot assume anything. You must call all the constructors, all the copy and move constructors, all the destructors. That's the default. Or you may decide to declare the type movable, meaning you can move this type in memory by using memcopy or memmove. So you only need to call constructors and destructors while creating instances. But if you have an existing instances and you want to move it in memory, just memcopy it over. That's fine. And there is also a further one, which is called primitive type, which is even one step beyond that. It means that every bit pattern is a valid object. So a primitive type is also movable, but that's something else. Okay, I'm not going to discuss it right now. So in practice, this is how it should work. You declare something like you create that int vector struct, which is our vector of integers, and after it, you declare type traits by using the macro. Remember to do it, because adding a trait after the fact, if you forgot, yes, it's certainly possible, but it's a possible binary compatibility break. So if you have strict ABI guarantees like Qt has, you cannot just patch after the fact. You must remember it when you create the type. Yep. So for each and every type you're going to put into a Qt container, remember to add this. There is a solution for this. I'm going to show it in a few slides. Okay. Let's keep talking about Qt containers, or in particular about Qt value types, and let's understand one of the design features of Qt containers. Qt containers and Qt value classes in general are implicit shared. So the title here says, understand implicit sharing, understand what it means, and be careful about something that we call hidden detaches. Be careful about what happens when things go wrong. So what do I mean by implicit sharing? That's just a buzzword. Yes, it is. Implicit sharing is a fancy name for reference counting combined with copy on write. Do all of you know about reference counting? Yeah, that's pretty much an established technique. Do you all know about copy on write? That's also an established technique. Yeah, so implicit sharing is the combination of the two. There's nothing new. A Qt value class implementation is typically something very simple. A Qt value class implementation is just a pointer to a payload. Inside that payload, we got a reference counter plus the actual data of the class. Yep. And during an object lifetime, we're going to manipulate that ref counter in the following way. So when you create an object, the ref counter is of course 1. When we copy an object, what we're going to do is put another pointer to the shared payload and increase the ref counter by 1. When we destroy an object, we're going to decrease the ref counter by 1. And if it goes back to 0, then it means, okay, now it's safe to deallocate the whole payload. When we call a const member function on a Qt value class, then we just call it. There is nothing to do about the ref counter. But here's the important part. When we call a non-const member function, then we must copy. We must check if the ref counter is greater than 1. Yes. Then please deep copy this structure. Yep. We call the operation of deep copying detaching from this shared data structure into my own copy. So here is it in action. I've got a vector of ints. Yep. The vector itself is just one pointer. It's a very small class that points into the actual payload. The payload contains the reference counter, some bookkeeping, and then the data, right? So that's the situation. Now I take a copy of a vector, and taking a copy is nothing more than setting a pointer and increasing the ref counter. That's surprisingly cheap to do in general, right? Unlike standard vector, for instance. Then what happens if I want to modify these containers? For instance, I want to change v2. The operation of the subscript operator, that's a non-const member function. So as such, I need to detach from the shared data structure. Yep. I need to make a deep copy. So what I do is that a series of operations, I will deep copy everything, decrease the ref counter of the original. Now I've got a new allocated chunk, so the ref counter is 1, and then I modify my private chunk. Yep. So v2 is now correctly modified and contains 99. Anything clear? Yeah, that's pretty much straightforward. Why is this good? Why has this been adopted by Qt? Well, first and foremost, because C++98. We did not have move semantics, so we wanted to make writing code simpler. We wanted to make, let's return containers by value. In C++11, that's for granted. Yes, we got move semantics, but back then we didn't. So we used this mechanism in order to cope with the complexity. We said, let's make it easier for developers to pass containers around, return them a value, pass them value sometimes, take copies without thinking twice. Because most of the time, you're just going to do some ref counter manipulation and not actually do any expensive deep copy. For this reason, the great majority of Qt value classes are implicitly shared. All the containers, except for var-length array, QString, byte arrays, variants, you name it, if it's a value class, 99% of the time it is implicitly shared and therefore cheap to copy. So all's good, right? Where's the catch? The catch is there are a few subtle bugs that might lurk in by the fact that these classes are using implicit sharing. I collected a few of those here, so let me discuss them one by one. The first one is a subtle bug that has to do with returning references to some data into a container. Here's the problem. If I have a reference to some data into a container, in theory, that container should be marked as unshareable. I should not be able to take cheap copies of that container any longer. Yep. And now I have some code to back up that statement. The problem is that we take references to data into a container all the time when we use iterators, when we use the subscript operator. So for that reason, basically, a trade-off was made to shed away correctness, in this case, for speed. So let's see where is the correctness problem. Here I create a vector with 3 elements, and I take a reference to the first element of that container. Yep, that's safe, that's okay. Then I copy the container. What's the situation at this point? The situation looks like this. I've got 2 vectors, v and v2, pointing to that shared segment with the ref counter true, and r pointing into the shared segment. Yep, that's because I took the reference to r before getting the second copy to v2. So what happens now if I modify the container through the r reference? Well, that's going to affect both containers, so the situation will end up like this. By modifying r, a reference to v, I modified v2, a container which should be a complete copy of v, right? That's not the case. So sometimes this may bite you, especially if you start having problems with aliasing, or you're just taking a couple of containers by reference, you're not sure if they're the same container, you may end up modifying one container accidentally instead of the other one. Yep, so that's one problem, sure. Let's see another problem. Suppose I got a function. This function is called calculate something. Yep, and this function returns a vector of integers. Okay, fair enough. Then I'll call that function. I call calculate something, but I'm not really interested into having all the results. I just want the first one, so I just call first. If your course first is like front instead of vector, that's the same thing. What's wrong with this code? Apparently nothing. Apparently this code works. Indeed, this code does work, but there is a subtle thing going on there. That is, first, just like front, is a non-const member function. If the vector returned by that function was implicitly shared and the ref counter was bigger than 1, this code right here just caused an accidental detach. So what I did was deep copying the vector, getting the first element, and then destroying the copy I just made. All in one statement. Not bad, right? Yeah. So there is a solution. The solution is easy. Don't call first, call const first, which is a const member function that will not detach. But these things are not so easy to spot in ordinary code, not easy to spot during code reviews. Typically, these things appear in heap profilers. If you have a heap profiler, this appears as like a transient allocation. You've got an allocation on a heap that lasts one statement. Yep. So you see a peak there, see what's going on. Oh, I am accidentally detaching. Nah, that's bad. But we can go even one step further. Not only this is a performance problem, this accidental detach may actually introduce subtle bugs in your code base. So let's see an example of that. I've got a map of integers to integers. I populate it somehow, and then I ask, does this map contain a key? So I use find of the key. That returns an iterator. Is the iterator at the end of the map? If it is, then of course the key was not there, otherwise the key was there. right? And if this was a standard map, you would be absolutely correct. But this is not a standard map, this is a Q map. So what could go wrong here? The thing that could go wrong here is that cend it returns a const iterator, so it does not modify the map, right? What happens if the map is shared? Find is going to return a non-const iterator. So in order to do that, it might need to detach the map and deep copy it. So what happens? You call cend first, and that returns perhaps the very end of the map. Then you call find. The first thing find is going to do is deep copy the map right away. And then it's going to perform the find algorithm, and perhaps it's not going to find the key. So it's going to return the end. The end of what? The end of a new copy of the map. So basically you have now two different ends returned on the two sides of the equal operator. The two ends will be different, so this code is going to be found, even if the key is not there. Yep. This is extremely subtle to find. This is extremely subtle to find doing a code review, but basically, okay, again, we got a solution. The solution is always called const find, but actually dealing with this sort of bugs in production code is very, very tricky. There is a solution coming in a few slides, don't worry too much, but yeah, this is the kind of things that may happen. So my advice here is this. You need to understand implicit sharing, because if you're using Qt, all Qt value classes are implicit shared. Just be aware of what you're doing. Be extremely aware not to fall one of these traps. The position of the standard library in this regard is very, very clear. Some containers in the standard library were or could be implemented in using implicit sharing in C++ 03. Since C++ 11, standard library basically forbids implicit sharing for all its containers. Qt will not move away. Don't worry about that. There is simply too much code written out there that relies on these mechanisms, relies on the fact that you can take a copy of a vector and that's cheap. So implicit sharing, again, is here to stay. Okay, let me even add another, just like nail in the coffin about implicit sharing, which has to do with iteration of the containers. So Qt has something called for each, or Q for each. That's its own version of iterating over a container. Just don't use it. In C++ 11, we got something better, which is called the range base for. Just be careful about how to use it. And let's see why. Here's the very definition. Well, it's not the actual code, it's the exposition of Qt for each loop. Again, this made sense in a pre-C++ 11 world where we did not have ranged for. So we had a macro that more or less expands to that. I got for each variable container, and then the body of the container, the body of the loop. What for each is going to do is evaluate the container expression and assign it to an object. So basically make a copy of the container. By the way, first statement. There is no reference there. That's taking a full copy of the container. Yep. This copy is const, by the way. Then I'm going to basically open up a couple of iterators over that container, actually over the copy, and then I'm going to iterate over the copy. Do you see that? Yep, I take the copy, iterators over the copy, and perform the iteration, and call the body every step. What is the problem with this? Well, this has endless problems. First, it takes a copy. So if I'm accidentally passing a standard library container there, this is going to cause a full copy of the container. If I pass a standard vector in there, this is going to copy a standard vector, and perhaps I don't want that. Actually, I almost never want that. The second problem is this is iterating over a const copy of the container. So a mutating loop is impossible. I cannot modify the container because those I and E will be const iterators. And what's worse, those are const iterators on a copy of the container, so they have nothing to do with the original. Yep, so it's just bad. Don't use this ever, okay? Con. Just don't use it. There is a pro, and I put it between quotes, Dr. Evil Pro. It's always safe to modify the original container from the body because you are iterating over a copy. Just don't do it. Forget that this exists. So don't use it. in your code base, if you're using Qt, define that macro, Qt no for each, which will disable the for each loop. And I'm going personally to remove this from Qt 6. So, yes. So just don't use it, okay? Why? Also because we have a better solution for this. We got a much better solution. The better solution, of course, comes with C++11. It's the range-based for loop. Yep. The syntax looks like that. It's for variable, colon container, then the body. This looks, when evaluated, again, just exposition only, that's not the actual code, but will turn out to be something like that. So you evaluate the container expression and you assign the result to a reference, not a copy, a reference. Then you call begin and end of whatever you just obtained, and then you iterate. This looks good, right? So let me ask, what happens if a container is, for instance, a standard vector of objects T? In this case, so C is going to be a non-const reference to standard vector T, and I and D, the iterators, are going to be mutating iterators. So now I can mutate the original container from within the loop. That's great. So let me ask one further question. What happens if container is QVector? In this case, C is going to be a non-const reference to QVector, and I and D are going to be mutating iterators into a QVector. So those, by definition, will need to detach the vector, because now I'm possibly modifying the vector. And this decision takes place before even considering what's inside the body. So what if inside the body I'm not modifying the container at all in the end? I'm just reading from it. Sorry, the syntax does not say that. The syntax says you're about to call begin and end over a non-const container. I'm going to deep copy it if it's shared. End of the story. So there is a possible detach happening here, even if you don't modify the container from within the loop of the body. Sorry, within the body of the loop. Got that the other way around. Yep, that's just the way it is. That's the syntax. And finally, what happens if instead the container is a const standard vector or a const Q vector? Well, in that case, C is going to be a const reference. Begin and end are not going to detach anything because what they need to return are non-const, non-mutating iterators, sorry. So const iterators. So everything is fine. Yeah. So to recap, this is the situation. The situation is that if you use Q for each and you accidentally pass in a standard library container, that's going to deep copy it because Q for each takes a copy. If you pass in a Qt container, everything is fine because taking a copy of a Qt container is fine because it's cheap. Forget that the first column exists. Don't use it. Okay, use the ranged for loop. So the second case is where I have a mutating loop, in which case, of course, I must pass in a non-const container, in which case it is okay to detach if I'm using a Qt container because this is a mutating loop. I need to modify the copy. If I'm creating a non-mutating ranged for loop, then beware that this might detach the container, even if you're not touching the container from without the body, from within the body. How do we work around that? There is a solution coming in C++17, yay. A solution is basically, if you got a non-const container, make it const and then pass it to the ranged for loop. A way to make it const is by using standard add as const, which is a new library feature in C++17. In Qt, we realized many people cannot wait for C++17 in their own toolchain, so we also have QsConst, which does exactly the same thing, converts a non-const al value to a const al value reference. That's perfectly fine. So this is the way you're supposed to do it. You create a vector, you populate it, and then you call a ranged for loop by calling a QsConst vector. Yep, this will never detach because the vector returned will be const. For various technical reasons, this QsConst does not work with R values. So if you've got an R value, the easiest solution is just capture the result somewhere in a local const variable and then pass it to the loop. All right. So many problems so far. Can we see some positive news? Yeah, so this talk will not be a downer, but let's see something good. There is some good news. There is the light at the end of the tunnel. Run Cladesy on your code base and fix its warnings. So what is Cladesy? Cladesy is an open source Clang-based tooling that will detect all the mistakes that I've just shown to you. It's open source, just go on GitHub, download it. It's pretty much like Clunked. How many of you have heard of Clunked or used it even? Yeah? So it's a linter. It's something that you can run on a code base, and this will fire warnings about Qt specific usages, or actually should I say misusages of API. And everything I just shown you about detaching temporaries, about mixing iterators, about forgetting type info, about using for each in your code base, Clazy these days detects that and will report that to you back as inform as warnings. And if you believe that you're so good that you're not going to need this, okay, maybe you are, but let me just leave you some numbers to you. We just an experiment ran Clazy on Qt itself. Yeah, and as of yesterday, there were over 9,000 warnings detected over Qt. Yeah, that number is the important part. So please be aware, it's extremely easy to fall into one of these traps. Luckily now we've got this tool. And something awesome about this tool is the fact that it also supports fix-its. So for situations in which there is a case, it will also suggest you how to fix it and possibly automatically refactor your code in order to fix the potential problem. Okay, right, that was great. So now for something completely different, let me talk a little bit about Qt string classes. In particular about a new one, which is coming in Qt 5.10, which is due to be released in a couple of months now, which is called QStringView. I'm pretty sure that you have heard in this very conference something called standard string view, right? Isn't that the most awesome thing ever? Yeah, it's also coming to Qt under this other form called QStringView. But before we get there, let's discuss the first part, understand the Qt string classes. So let's count all together. In how many ways I can create a string when using Qt APIs? Well, one first, yeah, too many, yes, too many. Yeah, in fact, these slides, this kind of slides is always misleading. So the first way is just like if you want char literal, I'm not going to consider this because this has nothing to do with Qt. So the first one would be something like called like that, QByteArray string, or perhaps something called QByteArray literal string. Or maybe something like QString string. Or maybe QLatin1 string. Or maybe QString literal string. Or maybe QString from Latin1 string. Or maybe QString from UTF-8 string. Or maybe TR string. Or maybe QStringView, and now I need to like Unicode UTF-16 string. That's lots and lots of ways of creating a string in Qt. Would you agree, right? Okay, so let me clarify a little bit about what's going on this slide, one block at a time. So in particular, let me discuss the classes that have been involved in here. The first class to discuss is the first guy called QByteArray. QByteArray is basically just a sequence of bytes, a byte array. It's not a string because it does not specify an encoding. And we know about something like this in the standard library, that's standard string. Yeah, this is the equivalent. It's just a collection of bytes. It does not have any encoding, and therefore, as such, it's not a string. It's a sequence of bytes. It is implicitly shared, just like as all of Qt value classes. And in particular, its constructors will allocate memory, just like as you would expect. Yep. Yes, there is a clutch. There is something called QByteArray from raw data that will avoid some allocation. Just don't use it. It's time for standard string view these days. In order to build a QByteArray without allocating, there is a direct support for something called QByteArray literal. That's going to build a QByteArray object without allocating memory. That's great, indeed. So if you have a function that expects a QByteArray and you just want to pass an instance of it without creating it every time, use the literal part of it. And in particular, use QByteArray in general just to store byte arrays. Don't store strings in there. Thank you. Okay, so similar discussion about QString. What is QString? QString, it is a string because it is encoded in a specific encoding. The encoding that was chosen for QString a long time ago was UTF-16. You may disagree with that decision. Sorry, it's too late to change it. This decision has been made 20 years ago, and there is simply too much code out there relying on that. We cannot go back and change it. The good news is this class is fully Unicode aware, so it supports all sorts of Unicode aware manipulations, unlike the standard library counterpart, which yes, stores UTF-16 code units, but it has no full support for Unicode. You will need an external library for that. Yep. So QString in particular, again, it's implicitly shared, its constructors allocate memory, and in particular, its named constructors, such as from UTF-8, from Latin1, we allocate memory. It has the same clutch, just like CppByteArray has, like that from raw data to have a non-allocating constructor, ignore it. There is QString view these days. And if you need a way to build a QString without allocating, now there is QString literal. QString literal will decode the data you pass in there from UTF-8 to UTF-16, and we build an entire string which is then going to be stored typically in the read-only data segment of your binary, of your executable. So QString is the class that you are supposed to use to store strings. Unicode strings, and in particular, all strings that the user is going to see on the screen or interact with. Yep, never use CppByteArray for that. How about the third one, QLatin1 string? This class is kind of unique in the sense that it is just a thin wrapper around a pointer and the sides, and nothing more. It does not manage anything. It's actually a literal type, according to C++ definition. The reason why this type exists is because we can implement things better when we can do some optimizations related to the fact that we know that a certain char star sequence is a Latin1 string. So for instance, if you take a look at the QString documentation, you will find that the starts with function, the function that detects whether a string has a certain prefix, has an overload for another QString or for a QLatin1 string. Why there is such an overload? Because we can implement the second one in a very efficient way. Yep. So if you just need to check whether a string starts with a certain sequence of Latin1 characters, you may avoid building a QString just for that. Yep. QLatin1 string has virtually zero overhead. Actually, it has zero overhead because it just passes a pointer and a size and nothing more. And we can do some serious optimizations in the code of starts with for Latin1 strings. Yep. If you're curious, ask me, but basically this on good processors boils down to do a loop around a couple of processor instructors. It's just a SIMD unpack and comparison. Apart from this, I mean, in QString, CppByteArray, there hasn't been much development. So if you're really, really curious about the usage, there is another great talk that has been given a couple of years ago that just deals with QStrings. I'm not going to go in further detail about QString, CppByteArray, because I want to talk very, very briefly about the new guy, which is QString view. So QString view is basically standard string view over QString data. Actually, I should say over QString-like data, because QString view is basically just a view, just a non-owning container over anything that looks like UTF-16 strings. So you can build a QString view over a QString, over another QString view, over a standard U16 string, over an array of char16T. Yep, you can pretty much build these guys out of anything. And the good news is that just like standard string view, this offers basically the majority of the Unicode const QString APIs without the need of constructing a QString first. So if you need to do const Unicode manipulations, you can apply them on top of QString view. How do I use it? Well, basically, the primary use case for these guys, for QString view, just like string views in general, is as an interface type. If you got a place in your code where you expect some Unicode string data, but you don't need to store it anywhere, use a QString view. Yep. Example of such API, we have something like that in Qt. Suppose you got like a document class, and this document class, you need to find a substring, and if you find it, return an iterator of where that substring appears in the document. So what kind of data should you pass in? What's the type of the substring that you want to pass in? You can choose. It could be QString, but if it's QString, that means you need to allocate that string every time you call that find function. That's not exactly good. It could be Q-byte array, but Q-byte array should never be used for doing string manipulations, so don't use it. It could be Q-late in one string. That works if and only if you want to limit yourself to late in one. In general, this is not good for finding any sort of Unicode substrings, right? So the proper solution for this would be QString view. QString view basically, it's Unicode safe, it never allocates, and moreover, you can build it from a huge variety of sources. So for instance, I have a document and I call find passing a Unicode string literal, just like that. No need to allocate anything. Or perhaps you do have a substring allocated in a QString that you want to find. Just pass that QString in. It will implicitly convert to QString view. Or perhaps you want to just pass in a substring of a bigger string. There's no need to allocate anything. Just build a QString view as a substring of a bigger string. That won't allocate memory. Yep. It's great. So we're going to use it everywhere. Another example that I have that I've been using Qt, that we're using QString view for in Qt will be as a alloc-free tokenizer. Suppose I got a big string and I want to run a regular expression over it. And every time I run the regular expression, I want to extract the substring captured by that regular expression. There is no need to allocate anything. The memory is already allocated in the string at the first line, right? So now we can finally return views into already allocated data. That's just great. So basically, QString view will be a game changer in Qt, pretty much just like standard string view is going to be would be a game changer in all of your C++ APIs. We have a problem, however, which is this, that in Qt we already have a huge number of APIs that take a QString and don't need to store it. So in Qt 6, in theory, they should all be changed in order to adopt a QString view. If you're looking for some contributions to an open source project, this will be great. So we'll need to take our patience and go around and fix use case everywhere. In Qt 5, there is also another class which I didn't discuss. It's called QStringRef, which should be what QString view is doing, but it doesn't for a number of reasons. I would recommend against using it. That's another guy that is going to be killed in Qt 6. So just stay away from that. Download Qt 5.10. It's coming out in 1 month, 2 months. So that would be just great. And now I think I got like 5 minutes for taking some questions. Thank you. No questions? Maybe. Yes, please. There is a microphone in the middle, so if you may want to use it, thank you.
I'd just like to add to the container classes that you use them. You have to keep in mind that the index is an int.
Yep. Yes. That's one. Yes. Yes.
For some people, that may be quite important.
Yes. So that's another of the convenience thing that was made a decision based on convenience, because it was thought that many people would be more familiar about having a signed integral type, not unsigned. Actually, that discussion I think is still going on in the C++ community, whether that unsigned is a good thing. But yes, it's just an integer. You cannot change it because it does not depend on your allocator or anything. It's just int everywhere. Yes, you are absolutely right. It's one of those convenience decisions. So in practice, if you're using QVector for building a GUI or something like that, that doesn't hurt too much. But yes, for business logic, they may hurt you very, very hard if you expect it to be big enough to store big numbers. Yes, definitely. Thank you.
Yeah, I was wondering, do any of the Qt containers define cheap initializers for their STL counterparts? If I want to, for example, make a QVector from a standard vector.
Unfortunately not, because there is no way of doing it really. You need to deep copy the vector. There is no, as far as I know, there is no API possible to like steal the guts. Yeah. It would be a good idea, yeah. It would be a, sorry. Say, yeah.
Yeah. So I mean, when you mentioned that some of the Qt containers were using STL implementations internally, I'm hoping, well, maybe there would be a way to take advantage of that.
Well, it's not that the Qt containers specifically are using STL internally. Some parts of Qt are stopping using Qt containers, and they turned towards the standard library containers because they're better. because they're faster, expand to less code, they're better tested and so on. The Qt containers still have their own implementation, which is incompatible with the standard library implementation. And as far as I know, there is simply no way from somebody to take a standard vector and like, okay, I'm going to steal your data now you're mine. I mean, we could add some crazy stuff about that if there's really the need. All you have right now is QVector from standard vector, which is like a named constructor that will deep copy the data anyhow because it needs to use it in the Qt specific way. Sorry about that. You're welcome.
This question is about Lazy.
Yes.
Will that catch QString literal and QLet one string misuse, like when they're when one's the non-optimal choice over the other?
It does have some checks about that. Yes, indeed. I think it will. No, I don't want to. I need to double check. What's the current status of the checkers because it's got like 70 of them. I think it will suggest late in one string. Whether you're calling a function which is overloaded for QLate in one string and you're passing a string literal. So it will tell you, please wrap this in a QLate in one string because in this case we can enable the fast path. You can also disable the QString constructor from const_star if you want to. There's just a marker you can define in order to basically be able to see that at a certain point in time you're building a QString. And so, okay, I'm allocating memory at this line, you know that, so you may be aware about what I'm doing and perhaps decide, okay, let me wrap this up into QLate in one string or QString literal if it's needed. So a combination of the two things is possible for you to be able to detect what's going on, yes.
Awesome. The second question I had was also about QString. So say QString is our string class of choice throughout the whole code base.
Mm-hmm.
Is there a level or some sort of demarcation where standard string starts becoming the preferred choice? Because you said use QString for Unicode strings,
yeah,
for storing Unicode strings.
And also for manipulating them. That's the big advantage. I mean, if you just need something to store UTF-8 or UTF-16 code units, then any container will be good. But the problem, I mean, what QString gives you is the manipulation, which is Unicode aware. So you can uppercase, downcase, compose, decompose, do all sorts of fancy stuff which needs to be Unicode aware, which is the stuff that the standard is still lacking in certain corners. So if you're using QString throughout your code base because you need to do these manipulations eventually, that's the reason. Otherwise, you don't need a string class, you just need a container of bytes. So the question was about, is it a good idea or?
Yeah, basically.
Yes, it is. I mean, because if you have a QString around it, it means I want this to be a Unicode string because I need to deal with it as a Unicode string. So use it, yes, definitely.
Thanks.
Thank you. They say that world domination starts with strings. So, yeah.
I just want to add something for the QString literal.
Yes.
Be aware it allocates, not allocate, but it stores its data in the data section. So if you have a DLL that gets unloaded,
Yeah.
that can get you in trouble. So just be aware.
Yeah, yeah. So this particular remark, the remark was about the fact that, what is it? QString literal is going to store the string that it creates into the read-only data segment, actually, of your binary. So what if you create such a string into coming from a DLL, from a plugin, from somewhere, and then you're going to unload the plugin that's going to unload the string. So if you still keep some reference around, that's going to just crash your program. Yes, that's true. We haven't found a good solution for that, but I think this is discussed in detail if you're really curious on that talk that I'm just going to reference because I don't want to repeat content which is already good on the internet. So please go watch that talk if you're specifically interested in all these quirks about QString and QString literal. So yes, thank you for saying that.
I saw many projects which use simultaneously standard containers and Qt containers.
Yep.
And do you think it's some kind of competition between two frameworks? And what do you think about which classes should be used? And did you make some tests? Which classes are faster and more efficient?
The standard library ones. They regularly beat the Qt ones, because they're more tested, more used by the bigger C++ community. And I would say the number one reason is the people writing the standard library containers are the same people writing your compiler. So those people know how to optimize those data structures because there's just that. So that's why also Qt is using the standard library containers inside itself, because they're better.
Do you see future of Qt containers? Putting aside QString, of course, it's very convenient class.
Yeah.
And then no one is arguing with that, and the rest is questionable.
Pretty much, yes. So Qt containers are here to stay because we cannot break applications. Sorry, I mean, actually, you should thank us or something like that, because we're not going to break your code, but consider moving away. So just keep using the Qt containers at the interface level when from your code you go into Qt or vice versa. For everything else, especially for your business logic, stick to the standard library one.
Thank you.
You're welcome. And now the session is finally over, so I'm going to just say thank you to all.